So, good evening, ladies and gentlemen, and a very warm welcome to Imperial College for what promises to be a fantastic evening celebrating the centenary of General Relativity. It's undoubtedly one of the most exciting events in our calendar this year, and one which has been the source of an almost unprecedented level of interest from our community of staff, alumni and friends. In fact, we had almost 6,000 people wanting to come along this evening, a remarkable number. Obviously, we couldn't fit everyone into this particular room, so I'd like to give a special welcome to those watching from the overflow rooms. It's great that so many people are able to be part of this special event. We're all here, of course, to mark 100 years, almost exactly to the day, since Einstein published his famous paper on general relativity, Die Fehlgleichungen der Gravitation, the field equations of gravity, regarded by many as the most perfect intellectual achievement of modern physics, indeed of modern science. For the last 100 years, physicists have been working with and testing Einstein's theory, using it to achieve a better understanding of the history, content, and fate of the universe, the origin of time, the motion, evolution of solar systems, stars, galaxies, and so on. A universe that expands forever, black holes, wormholes, time travel. General relativity has allowed scientists' imagination to take flight with new possibilities to be worked on, examined, and tested, revealing a universe that is much stranger and arguably much more beautiful than we could ever have imagined. And of course, it is not all the stuff of cosmic wow factors. Closer to home, the gravitational frequency shift on GPS clocks due to general relativity is measurable and needs to be corrected for. Now, Imperial College has played a key role in many of these developments, not least through the work of the Theoretical Physics Group in our physics department here. The group was founded in 1956 by Nobel Prize winner Abdus Salam and carries out research in cosmology, fundamental quantum theory, quantum field theory, and string theory. And it's a great honor to welcome members of Abdus Salam's family here this evening. Now, of course, we had hoped that Professor Stephen Hawking would be present to deliver a lecture this evening. We were all saddened to learn that Stephen has been unwell recently and is unable to be here with us today. So on behalf of everyone at Imperial College, I would like to wish Stephen a very speedy and full recovery. Stephen very kindly sent through a voice message, which I'll play to you in a moment. But first, I already alluded to Imperial's outstanding strength in this area of scientific endeavour. I am delighted, therefore, that two of our leading theoretical physicists have agreed, at rather short notice, to deliver lectures this evening and to participate in a question and answer session immediately afterwards. Our first speaker is Faye Dowker, Professor of Theoretical Physics here at Imperial. Faye did her PhD in Cambridge under the supervision of Stephen Hawking, graduating in 1990. She subsequently held research positions at FermiLab in Chicago, University of California, Santa Barbara, and Caltech, before returning to the UK to join Queen Mary University of London and then Imperial in 2003. Her current research focuses on the causal set approach to quantum gravity. Now, as many of you will be aware, Faye is a regular media contributor. You may have heard her, for example, on The Infinite Monkey Cage with Brian Cox and Robin Ince, including a memorable broadcast from the Glastonbury Festival in 2013. The title of Faye's talk is Inner Space, Outer Space, a meditation on general relativity. Our second speaker will be Jerome Gauntlett, Professor of Theoretical Physics and head of the Theoretical Physics Group at Imperial, where his research focuses on string theory, black holes, and quantum field theory. Jerome moved from Australia to Cambridge to carry out his PhD in Stephen Hawking's relativity group, graduating in 1991. He then held research positions at the University of Chicago, Caltech, before returning to the UK, first to Queen Mary, University of London, and then to Imperial in 2003. Jerome also has a high media profile. Not many people know, because presumably they were halfway out of the cinema by the time it rolled up on the credits, that Jerome was the theoretical physics consultant to the Oscar-winning film The Theory of Everything. As such, he wrote up most of the equations on the blackboards in various scenes, and he tells me that he enjoyed meeting and talking with Eddie Redmayne, the actor who won, of course, an Oscar for his role as Stephen in the film, and he even gave him a crash course in black hole physics. The title of Jerome's talk is Black Holes and the Unity of Physics. Now, I mentioned earlier that although Stephen Hawking is not able to be with us here in person this evening, I think it is a measure of how much he was looking forward to the occasion that he's very kindly recorded a short message for us, which we will play now.
Theory of General Relativity. Albert Einstein was the greatest physicist of the 20th century, and his discoveries revolutionized our understanding of the world and our place in it. Although I cannot be there, I know you will be in very good hands with students who trained in my relativity group, Professor Faye Dowker and Professor Jerome Gauntlett. The Theoretical Physics Group at Imperial College has a great tradition in carrying out research in fundamental physics since its founding by Abdus Salam, and I look forward to visiting on another occasion.
So, on those kind words from Stephen, it gives me great pleasure to introduce our first speaker, Professor Faye Dowker.
Good evening, everyone. It gives me such pleasure, and I'm so happy to talk here on this occasion to celebrate the 100th anniversary of general relativity, Einstein's theory. GR, for short, is our best theory of gravity. And using it, we are able, as James described, to understand and explain many phenomena in what we might call outer space, including the motions of the planets, neutron stars, black holes, galaxies, and the structure and evolution of the cosmos on the largest scales that we can observe. And one such system in outer space that general relativity does a very good job at describing that I want to highlight is the Hulse-Taylor binary pulsar. I want to highlight it because I'm going to come back to it later on in my talk. So the Hulse-Taylor system is a system of two neutron stars which are orbiting each other, and the period of this orbit is roughly 8 hours. And the Hulse and Taylor made the discovery. They discovered this system in 1974. They won the Nobel Prize for this discovery in 1993. And so we've been observing this system for over 40 years now. And over that time, the period of the rotation of the two neutron stars around each other has changed, very, very slightly, but detectably changed. And general relativity precisely and accurately predicts exactly that change in the orbit, the periodic orbit of these two neutron stars. And later on in my talk, I'm going to come back to the Hulse-Taylor system and tell you what general relativity says is going on, how general relativity can explain why the period is changing. Tonight, however, what I want to do is to argue and hopefully convince you of that general relativity also does a very good job of explaining and accounting for our inmost private experiences. So if you like, you could call those the phenomena of our inner space. And to do that, we're all going to participate tonight in a general relativity experiment that we can do here in this room, and you won't even need to leave your seat. And I hope that it works. I'm reminded of the old joke about experimental science, which is, if it moves, it's biology, if it smells, it's chemistry, and if it doesn't work, it's physics. So I hope that you will be convinced that general relativity accords better with your experience, your inner experience, than the theory of gravity that preceded it. That theory of gravity was Newton's theory of universal gravitation. So we're going to do a direct comparison between these two theories, what general relativity says and what Newton's theory of gravitation says. So because it's going to be this comparison, first of all, I have to tell you what the Newtonian theory of gravity says. So at the time of Newton, the body of data that was crying out for a physical explanation was all of the observations that had been made on what people called celestial mechanics, and in particular, the orbits of the planets around the sun. So here's the Earth orbiting the sun. This picture is not to scale, obviously. And Johannes Kepler had proposed a way of understanding of a set of rules that summarized the data very well, but what was lacking was some physical explanation of why the planets orbit the sun. And the Newtonian theory of universal gravitation proposed that we can understand why the planets orbit the sun in terms of a force. So Newtonian gravity says that between every two objects in the universe, there is a force of attraction. It's very precise, very quantitative. The theory tells us exactly how big that force of attraction is, and it's proportional to the masses of each of the two objects and inversely proportional to the distance between them. So the more massive they are, the bigger the force. The further away they are, the smaller the force. So why does this force of attraction that the sun exerts on the Earth, why does that explain why the Earth goes around the sun? Well, we can just compare that to this simple system of this ball. So this ball is going around my hand in roughly a circle. And why is it doing that? It's doing it because there's a force on the ball, and that force is exerted by the string. It's the tension in the string pulling the ball, and the direction of the force on the ball is along the string towards my hand. So the Newtonian theory of gravity says that in exactly a similar way, this force of attraction that the sun exerts on the Earth and all the other planets causes the planets to orbit the Earth. And because it was very precise and very quantitative, it was extremely successful. It accurately reproduced all of the data that had been gathered by astronomers on the planetary orbits. But more than that, it was also predictive. So, for example, the planet Neptune was discovered by comparing the Newtonian prediction of the orbit of the planet Uranus to where it actually was observed to be. And it was found that there was a slight discrepancy. And the discrepancy could be explained if there were another planet, one that hadn't been observed yet, out in an orbit beyond Uranus, and the Newtonian theory was able to predict exactly where this new planet should be found. And then when astronomers went to look, indeed they found it. So successes like this, particularly splendid new predictions that were verified, like the existence of a new planet, made people very confident that the Newtonian theory was right. It found widespread acceptance. Physicists used it all the time in order to understand the structure and evolution of our solar system. However, not everyone was happy with the theory, with the Newtonian theory, and it had major critics from the very moment that it was created, or that it was proposed by Newton, and including from some of the major thinkers of the day. So and one of the most accomplished and brilliant scientists contemporary with Newton criticized the Newtonian theory in the following way. So this is a pretty scathing assessment of Newtonian gravity. So he said, this scientist, that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. So that was just, this is absurd. The name of that scientist? Isaac Newton. And this, he wrote this in a letter dated only 5 years after the publication of the theory of universal gravitation. Now, the problem with the theory of universal gravitation that Newton is referring to here is a problem that came to be known as action at a distance. We can understand action at a distance by imagining what would happen if the sun suddenly moved its position. So if the sun suddenly jumps from where it is to somewhere else, then the force that it exerts on the Earth also instantaneously changes. And so at that very instant that the sun moves, the Earth's orbit will suddenly change. So we can just move the sun up. The Earth's orbit is now a different orbit, so that the Earth will start going in a different, along a different orbit. So this action at a distance was, if you like, a philosophical problem with the Newtonian theory of gravity. It bothered Newton, but because the Newtonian theory was so successful in predicting where the planets were going to go, people didn't bother with the philosophical problem. They brushed it under the carpet because they were so busy using the theory in order to do science with. However, that situation lasted for over 200 years until 1905, when Albert Einstein formulated a new conception of space and time in order to understand a large body of experimental results on electromagnetism. And this new vision of what space and time are goes by the name of special relativity. And the most famous consequence of special relativity is that light travels at a certain finite speed, and nothing in the universe can travel faster than that. So there's a speed limit, a universal speed limit in the world. No physical influence can travel from here to there faster than light can travel from here to there. So now there's a real contradiction, more than just a sort of philosophical niggle. There's a contradiction between this speed limit, the universal speed limit of the universe, and the Newtonian theory of universal gravitation. We can imagine what would happen if the sun jumped. The sun is so far away from the Earth that light takes 8 minutes to get to us, to get to the Earth from the sun. So if the sun suddenly moves, then we won't see it in its new position for a full 8 minutes. Light will take 8 minutes to get to us. But we'll be able to tell that the sun has moved, and the Earth will start moving on a different orbit instantaneously, before the light has a chance to reach us. So this physical influence on the Earth will have propagated instantly, faster than light can propagate from the sun to the Earth. So this is a real crisis. Newtonian gravity violates the universe's speed limit. It took Einstein 10 years to resolve this crisis, and we are going to walk in his footsteps tonight by taking some of the first steps that he took along the road to discovering general relativity. And to do that, we're going to do an experiment. And because that experiment is to do with our inner subjective experiences. In order to do the experiment, I'm going to need some volunteers who are going to tell us what it is that they experience. All right, so there are 4 seats here, so I need 4 volunteers from the audience. So if you are willing to volunteer, please put your hands up, and I'll choose 4 people to come up. Come on. Okay, yes. The 2 of you there on the end. Yes, you, sir, please. And yes, you, madam, please. Yeah. Or sir. Sorry, I can't. I absolutely can't see you because the lights are in my eyes. So sorry about that. Yes, please do come up and be careful of the steps because they're a bit steep. Okay. All right. Now, because this is experimental science, I've got my lab book here, so I'm going to write down all the results. So I'm going to take your name. So, in fact, let me introduce you to the audience. Please do have a seat, all of you. And just tell us your name and pass the microphone along. So,
hello, I'm Christopher.
Christopher, okay.
Good evening, my name's Guy Bowles.
Guy.
Hi, I'm Ellie.
Ellie.
I'm Lara.
Lara. Okay, good. Very good. So sit there for a minute. Now, we're all going to do the experiment together, so not just our volunteers here. Everyone is going to do it. And what it consists of is we're going to have to pay attention to sensations in our bodies. And with as little mental commentary and analysis as possible, right? So, and I found that in order to do that, in order for that to work as well as possible, it's useful to do a little meditation beforehand. So you might have thought that meditation was some kind of just a nice title, but in fact it really means that we're all going to do some meditation now. So when we meditate, it's a way to sort of switch off the mental chatter, and a device that's often used is to concentrate on one simple thing. And the device I'm going to use is concentrating on our breathing. And if any of you have done any mindfulness meditation, then that might be a familiar thing to you. Okay, so if you would like, you don't have to do the meditation, absolutely, but if you would like to, I have found that it does help in doing this experiment. So if you would like to, I invite you now to sit up straight in your chairs. Make yourself comfortable, but with an alert posture. And close your eyes. And concentrate on your breathing. Feel your chest rise and fall as each breath enters and leaves your body. Think of your attention as a spotlight. So this spotlight is illuminating your chest as you're breathing in and breathing out. And if you find that your mind is wandering, which tends to happen, you can just gently shepherd your attention back to your breathing. And each breath in is a new beginning, and each breath out is a letting go. Now take the spotlight of your attention and move it slowly down through your body, past your diaphragm, through your stomach, until it reaches your bottom. So your attention is focused on your bottom. And just be aware of all the sensations in and on your bottom. And again, if your mind is wandering, just bring it slowly and gently back to your breath. And then move your attention downwards to rest at your bottom and all the sensations that are there. And finally, move your attention back up through your body to your chest and take a deep breath in and out and open your eyes. Okay, now the question I'd like you all to ask yourselves is, what sensations were there? What sensations did I have in my bottom? In and on my bottom, that's the question. And I'm now going to do the science bit here. We're going to take the data that our volunteers are going to answer this question. So, Lara, can you tell me anything, absolutely anything? What sensations were there?
Just, I guess, as I
Oh, sorry, I need to give you the microphone so everyone can hear. All right, here you go.
I guess as I focused on it, I noticed
Yeah.
like the actual weight and like the contact with the chair.
Okay, contact with chair. Okay,
Yeah.
contact with chair. What did that feel like?
Heavy, I guess.
Heavy. Anything else? Can you give me a direction? Just say
Downwards.
direction.
Downwards.
Downwards, okay. Have you studied physics?
Yes.
That might be a problem, right? Okay. All right, Ellie. Yes.
Well, she took my main one, but you can
All
also
right.
kind of like, after a while, you're more aware of your clothes. I don't know, like just like my shirt and my leggings.
Clothes, okay, all right.
But yeah.
Leggings are legs, I think. Bottom, I need to,
Bottoms.
yeah.
Okay, yeah. So
Yeah.
mainly just kind of shirt, and also this like the very bottom bit of the chair, and
Okay.
just chair in general.
Chair in general. I have to say, you're interpreting the feeling. I want you to tell me just physically what you feel. Chair is that's too thoughtful, right? That's too theory laden, right?
Okay.
Just the feeling, that was the sensation.
Yeah, like kind of being pushed up.
Pushed up. Okay, all right, good. Okay, Guy, can you...
I felt the weight. I felt
Okay, tell me what
balanced.
you felt the weight.
Yeah.
What does that feel like? What?
comforting.
All right. Okay, good. Yep, excellent.
And balanced and centered.
Right. Rather high-level concept, I think, balanced, centered, and comforting there. I want something more raw, visceral, okay?
I felt contact.
Contact, direction, give me a direction.
Down, I suppose. Down.
Okay, all right, okay. All right, Christopher? Yeah.
Pressure perpendicular to the plane of contact.
What direction?
Perpendicular to the plane of contact.
Yeah, but which direction?
Oh, well, it depends on the different parts, but
Yeah.
overall up.
Just what did you feel? What did you feel?
The resultant force is up.
Up. Okay. All right. Okay. Very good. Okay. Thank you. Now, please let's give our volunteers a round of applause. Yes. Yeah. That's fine. Yeah. All right. Okay. Now I have to say, it didn't work too well. Okay, but I did get, okay, so we've got 2 downs and 2 ups, all right? So what I was looking for there was the answer that, and I absolutely can't see you, so we can't do a straw poll because I just can't see who will put their hand up. But what I was looking for there was the answer that you feel pressure from the chair pushing you upwards, all right? And I have to say that what my mistake was to bring people up who have obviously some training in physics, right? Physicists always get this wrong because they overthink. They have the theory, they actually have Newton's theory in their minds. So the idea is to get rid of all preconceptions, and I claim, and now you just have to believe me, that when I do this in general, the consensus is indeed that people feel a pressure upwards on their bottoms from their chairs. All right, that's my, I'm going to claim that now, and you have to just believe me. And what Einstein realized is that so Newton's theory says that there's a force on you pulling you down towards the center of the Earth. This attraction that the Earth has on you, this force of attraction, is pulling you down. That's Newton's theory says there is such a force on you right now, pulling you down. I claim that if you really attend to what you actually feel sitting in your chair, you don't feel any such force. What you actually feel is pressure pushing you up. And what Einstein realized is that there is no force pulling you down. There is only a force pushing you up. That's a genuine, real force that you can feel. The chair is pushing up on you, but there is no force pulling you down. And this was the first step towards building the theory of general relativity, and Einstein called it the happiest thought of his life. And I claim that you have always known it. You have always known that the Newtonian theory is wrong, that there is no force pulling you down, and you've known it in your bones. You've known it every moment of your life because you've always felt the ground pushing up on your feet, the chair pushing up on your bottom, and you have never in your life experienced any force pulling you down. I don't want to show you that yet. Okay, now we have a problem. Einstein had a problem, which is, well, if there's no force of gravity, no gravitational force of attraction between one body and another, then what causes the planets to orbit the sun? And here, Einstein had exactly the theoretical tool that he needed. And the theoretical tool that he needed was the concept of the field. Newton could not have made the advance that Einstein made because Newton didn't have this concept. Einstein had it, and it was ready and waiting for him to create general relativity from. Now, what is a field? There is, right now in this room, a substance, a material thing called the electromagnetic field. It pervades space and time, and we know it's there because we see its effect. In fact, light, everything that you see is because light is reaching your eyes from the objects that you're seeing. And light is oscillatory disturbances in this electromagnetic field. The electromagnetic field was introduced to physics by Michael Faraday and James Clerk Maxwell. And Einstein and his generation of physicists were very aware of it. They grew up with it, they were trained in it, and were very impressed by it. Electromagnetic fields solve the problem of action at a distance between charged objects. So two electrons repel each other. And before we knew about electromagnetic fields, it was thought that that was an action at a distance. This electron pushes this electron away. If you move this electron instantaneously, this electron will respond. But when electromagnetic fields were introduced, that action at distance goes away because when you wiggle this electron, what actually happens is that this disturbance in the electromagnetic field that's caused by wiggling this electron propagates from this electron over to this one, and it propagates at the speed of light because it is essentially light. So what Einstein knew that he had to discover was the analog for gravity of the electromagnetic field. He had to discover the gravitational field. And what he discovered was that the gravitational field is not like the electromagnetic field. It's not a substance that pervades space and time, but it is space-time. So the gravitational field is a four-dimensional fabric. It is curved by the matter in it. And here, in order to understand how this can create the illusion of a force, the analogy of a stretched rubber sheet is often used. So if you imagine stretching out a rubber sheet horizontally, placing a heavy thing like a bowling ball in the middle, that will distort the rubber sheet. And then if you roll marbles around on the rubber sheet, they will behave as if they're being attracted to the bowling ball in the middle. They're not being attracted to it at all. They're just responding to the curvature of the sheet. And in a similar way, the Earth responds to the curvature of space-time that the sun produces and orbits the sun as if it's attracted to the sun, but isn't really. It's just responding to the curvature of space-time. This theory of general relativity explains all the solar system data that the Newtonian theory describes, and more, much more. For example, let's come back now to the Hulse-Taylor system. The Hulse-Taylor system of the two neutron stars orbiting each other, those neutron stars create ripples in the fabric of space-time which spread out like ripples on a pond, carrying energy with them. And because the system is losing energy, the orbital period of the system changes, and we can predict precisely what the changes in the orbital period will be. Now, in the final part of my talk, I want to bring out what is perhaps the most revolutionary aspect of general relativity. And it's something that cannot be captured by the rubber sheet analogy. The rubber sheet analogy is an analogy for curvature for a curved space. But what is curved in general relativity is space-time, four-dimensional space-time. So here is a picture of a chunk of space-time. And everything that happens in the universe happens in space-time. And the way that I've drawn my picture is that the events that are in the past are down here, the events that are in the future are up there, and time passes as you go up the picture. So everything that happens in space-time. So here is an event that happens in space-time. That is me being born. Here it is, located at some position in space-time. Here's another event in space-time. This is me dying. And every event of my life, from my birth to my death, can be plotted out in space-time. It exists in space-time along what is called my world line. So every event of my life, one after another, lies along this world line that I am tracing out right now in space-time. Here is another birth, another death, someone else's world line traced out in space-time. Here is the event where we meet. Here is a world line of a photon of light that's produced in some star, travels through space-time, and I observe it here on my world line. Everything and everyone in the universe traces out their world line in space-time. And all of those events, past, present, and future, exist in this sort of timeless way in what people call a block view of the universe. And here we can see that this view of the world, the view of the universe in general relativity, is at odds. It doesn't accord with our inner experience. We experience time passing. That's the most fundamental aspect of our experience, is that we experience time passing. And here we can see the playing out of an ancient dichotomy. These quotations here are from ancient Greek philosophers who were thinking about the world 2,500 years ago. And already there's this distinction between two points of view. One, Parmenides said, the world neither was nor will be, it simply is. And the other, Heraclitus, said, everything changes, nothing remains still. This ancient dichotomy between being, this block universe point of view, and becoming, where time really passes, is still with us. And today it's present in a struggle to understand general relativity and space-time at a more fundamental level. Maybe our inner space is speaking to us of the next step beyond GR towards a deeper understanding. And for my part, I believe that that is so. And this is something that informs and inspires my own research on the deep structure of space-time. So inner and outer space are intertwined in our explorations of the physical world, Newton had this inner feeling that his theory was screwy. There was something wrong with it. But it took 2 centuries of experimental exploration to create electromagnetism so that Einstein could take the next step to understanding how and why gravity doesn't require a force. So general relativity was created through an interplay, an intertwining of inner and outer space. And I will end my talk there, but I'll give Stephen the last words. For me, physics is about seeing further, better, and deeper. Thank you for listening.
Physics seeks unity in nature. Isaac Newton realized that the apple falling to the Earth and the moon orbiting the Earth, although seemingly different phenomenon, are different manifestations of the phenomena of gravity. Faraday and Maxwell in the 19th century realized that the apparently different phenomenon of electricity and magnetism were part of the unified theory of electromagnetism. And in 1915, Einstein made the great leap that gravity actually is the manifestation of the unification of space and time, as we just heard in the previous talk. We've made great progress in unifying physics, but that quest for unification in physics is not yet over. We know that in addition to general relativity, our best theory of gravity, there's also a quantum world. And at the moment, we don't know how the quantum world is reconciled or unified with the theory of general relativity. What I would like to do tonight is to tell you something about one of the most astounding predictions of general relativity, which is that black holes exist in the universe, and present the case that black holes are the key to understanding what the next step in our quest for unification is. In giving a public talk, one of the golden rules is never ever to write down an equation. Tonight is a very special occasion, and I'm going to make an exception, because tonight we are celebrating these equations. These are the equations that Einstein wrote down in 1915 after 10 years hard struggle, 10 years sometimes making brilliant insights, sometimes going down dead ends, sometimes literally making errors, before he actually finally came to the final conclusion on November the 25th, 1915. It's no understatement to say that these equations have transformed our understanding of our position inside the universe, have transformed our understanding of nature at the deepest and most profound level. It's also no understatement to say that they are one of the jewels of all human knowledge and culture. So what do they say? Well, in a very precise mathematical language, they say that the curvature of space-time is related to the distribution of matter inside that space-time. And we had some examples of that in the previous talk. There's something else that's very interesting about these equations, which you can see right in front of you, which is that the letters G, capital G, and the letter C appears there. The letter C is the speed of light that we just heard about. The speed of light, which is so central, a central foundation of Einstein's special theory of relativity. It's the speed limit of the universe. The letter G that appears there is within the Newtonian framework of gravity. It governs the force between two objects. So this capital G gives you the precise answer for what the force is within the Newtonian framework. And the fact that the letter G and the letter C is appearing in Einstein's equations is an exact reflection of the fact that Einstein did a remarkable thing of unifying the Newtonian concept of gravity with special relativity, or subsumed those two theories into his beautiful and brilliant theory of general relativity. These equations were written down in November the 25th, and within a month, the first solution to these equations was constructed. And it was a solution constructed by Carl Schwarzschild, who found the space-time, or found a solution to those equations which corresponds to the space-time about a star. So the star, as we heard previously, bends space-time in much the same way that a very heavy object, for example, a cannonball, bends a rubber sheet when you place it on top of it. It's quite remarkable to think that Schwarzschild got a hold of Einstein's equations, managed to understand them, and found a solution all within a month. Quite remarkable. What's truly remarkable, he did all of that while he was a soldier for the German army on the Eastern Front in the First World War. He wrote a very eloquent letter to Einstein announcing his discovery, and he said this: "As you see, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." Perhaps the most remarkable thing of all about what Schwarzschild discovered is his space-time, or the space-time solution that he found, not only describes the space-time around stars, it also describes the space-time of black holes. But this fact, or the appreciation of this fact that he had found black holes, took about 50 years before it was properly understood and accepted by the scientific community. And it took longer still after that to actually be convinced, or the scientific community to be convinced, that black holes really exist in the universe. How would you create a black hole? One way would be to take the Earth and scrunch it down to the size of, in fact, a pea. If you manage to do that, you will have formed a black hole, a region of space-time that's so curved that light can't escape it in the context of general relativity. Well, that's very difficult to do, but nature's found other ways of making black holes, and one way is through the evolution of stars. The evolution, or the history of a star, is basically a balance between the matter in the star wanting to fall in on itself, and the enormous pressure that's caused by the burning of nuclear fuel deep inside the core of the star. And for most of the evolution of the star, these two things are balanced. The wanting to fall in on the space-time itself, and the pressure pushing the matter up. But when the nuclear fuel runs out and the star stops burning, and if the star is big enough, the matter in the star will fall in on itself and keep falling until it forms a black hole space-time. Here is a picture of a black hole space-time. And the key feature of a black hole space-time is that it's surrounded by an event horizon. In this picture, I've only drawn 2 dimensions of space, but of course we live in 3 dimensions, left, right, back, forwards, up and down. So the event horizon is actually a sphere. It's not a circle as I've drawn on this diagram. The event horizon is a place of last return. You can fire a rocket and go inside the black hole event horizon. You can shine a light beam and it will go inside the event horizon. But once the rocket's inside the event horizon, it's passed inside the black hole, it won't be able to get out no matter what you do. Similarly, if you're inside the black hole and you shine your light beam, that light will not go outside to the outside world. It will stay inside the black hole. I'll come back to what's deep inside the black hole a little bit later in the talk. How do we know black holes exist in the universe? Well, because they're black in the context of general relativity, no light gets out. So if you try to look at them directly with your telescope, you won't see them. They're not emitting any light. However, there's indirect ways to find evidence for black holes, and we have a lot of indirect evidence. And we think, for example, that there is a black hole that's in the center of our galaxy. Our galaxy is the Milky Way. It contains 100 billion stars. And our sun is just one of the stars in this 100 billion stars that make up the Milky Way. This is an artist's impression of the Milky Way, built from astronomical observation, and it accurately predicts, or roughly predicts, or shows where the Sun is and our solar system is in the context of the Milky Way. The solar system is really big. From the Sun to Neptune, it's 4.5 billion kilometers. And it takes a long time for a probe to go from Earth all the way out to Neptune, our most distant planet in the solar system. The solar system is big. But the Milky Way is huge. If you imagine our solar system for a moment is the size of a 10p coin, the Milky Way is the size of, well, it's in fact the size of the United States of America. The Milky Way is a massive, massive object. At the very center of the Milky Way, we're almost certain there is a supermassive black hole weighing 4 million times the mass of the Sun. The center of the Milky Way is near the constellation Sagittarius in the sky. As a boy growing up in Australia, I built myself a little observatory, and I used to spend hours looking at the night sky. If you haven't been to the outback of Australia and looked at the stars, I recommend that you do it, or try to do this sometime in your lifetime. This picture actually is a fairly good representation of what you'll see when you're deep in the outback on a cold winter's night in Australia. Well, how do you find the center of the Milky Way? Well, you should look for the constellation of Sagittarius. Sagittarius, the zodiac centaur archer with his bow and arrow. Well, don't look for that object. Trust me, look for Sagittarius the teapot. Look for Sagittarius the teapot and find the spout of the teapot and then go about the distance of the spout again, and you'll end up roughly at the center of the galaxy. Well, over a number of decades, astronomers have been looking at the motion of stars very close to the center of the galaxy. And what they've observed is that there's stars that are orbiting something right in the middle of the galaxy. And by looking at those detailed orbits of these stars, they can deduce that the mass of the object is 4 million times the mass of the Sun. No light's being emitted there, it's black. And again, by looking at the orbits as they come very close to the center, you can establish how small this object is. It's incredibly small, incredibly heavy, and it's black. It's almost certainly a supermassive black hole. There's other evidence for black holes, which I won't go into now, but this combined body of evidence strongly suggests, or the consensus of the scientific community is that there is a black hole of similar proportions in almost all of the galaxies, or most of the galaxies in the universe. There's about 100 billion galaxies in the universe, each with 100 billion stars, and the majority of those have a supermassive black hole in the center. Well, that's a lot of black holes. Black holes really do exist and are key components of the composition of our universe. In the 1960s, when Stephen Hawking was just beginning his scientific career, Stephen Hawking and Roger Penrose made a very interesting discovery about general relativity. Using those equations that I wrote down at the beginning of the talk, they proved that inside any black hole, there is what's called a space-time singularity. A space-time singularity where the laws of general relativity break down. And there's two things that's interesting about this that I want to tell you about. The first is that the singularity is not a point in space. It's not a place. Singularity in space could be in the middle of this stage here, and I can move around a point in space and I can avoid it. The space-time singularity is a singularity in time. It's like tomorrow. We can't avoid tomorrow happening. No matter what we do, Tuesday's going to happen. And the space-time singularity is exactly like that. It's exactly like Tuesday. Once you enter the event horizon, the singularity will happen. If we take the supermassive black hole at the center of the galaxy that I mentioned before, you can do a calculation, and you find that it takes, once you cross the event horizon, it'll take you about 60 seconds, about a minute, before the singularity happens. Interestingly, if you do anything else, if you forget your general relativity, You're inside the black hole, and you say, I'm getting out of here, and you fire your rockets desperately trying to get out. Ironically, all you will do is hasten your demise. The singularity will happen quicker if you try and do anything else. So a top tip for the interstellar traveler, if you cross the event horizon, just relax. Enjoy the ride. That's the best you can do. So that's the first thing that's interesting. The second thing is that I said that the space-time singularity means that general relativity is breaking down. And at first, hearing that sounds bad. Maybe Einstein missed something. His theory is incomplete. But in fact, this represents a profound scientific opportunity. We know that in addition to general relativity, there is a quantum world, which I haven't said much about yet, but there is a quantum world which governs all subatomic processes. We don't yet know how to unify the quantum theory fully with general relativity. The significance of Hawking and Penrose's result is they are telling us exactly where we need to look to unify general relativity and quantum mechanics. We need to think about space-time singularities inside black holes, or more generally, just think about black holes. That's the great result or conclusion of their observation. Another of the great insights or ramifications of Einstein's theory of general relativity is that it provides the foundation for us thinking about cosmology on the bigger scales. Big Bang cosmology is a space-time solution of Einstein's equations. The Big Bang cosmology says that the universe started in a very hot, compressed state and underwent some enormous violent explosion and started expanding. As that hot plasma expanded and cooled, galaxies formed, and those galaxies now are moving away from us in all directions. Penrose and Hawking, at a very similar period, established that just like in the center of a black hole, there is also a space-time singularity at the very beginning of the Big Bang. So in addition to black holes, we should be looking to Big Bang cosmology to also go beyond general relativity and quantum theory and seeking to unify these theories. The next step is now leaving general relativity, its framework itself, and adding in quantum theory, which I keep mentioning. Quantum theory is built on the, one platform of quantum theory is Heisenberg's uncertainty principle. Quantum theory provides our best explanation of all atomic and subatomic matter. Atoms, protons, neutrons, electrons, all subatomic particles, all the way down to the Higgs boson discovered in 2013, are described very accurately by quantum theory. One feature of quantum theory that I want to mention is that empty space-time is not as empty as you might think. Empty space-time actually is a froth of virtual particle and antiparticle pairs being created, existing for a little while, consistent with the uncertainty principle, and then annihilating. So we might have, for example, an electron and the anti-electron spontaneously coming out of nothing, existing for a little while, and then annihilating. We could have a proton and an antiproton spontaneously coming out of the vacuum, existing for a little while, and then annihilating. We call these processes virtual because we don't measure those particles when they're going through this dance I just described. However, there's indirect ways to establish that what I said happens, and we're sure these processes are going on. Well, Stephen Hawking, in the 70s, had the great idea to think about this precise process in the context of a black hole spacetime. And what he found was something very startling that we still don't understand the full ramifications of. Away from the black hole, the process I was describing continue to happen in much the same way. But near the black hole, near the event horizon, the spherical event horizon, sometimes one of these particles gets ripped apart and pulled into the black hole and then goes down and the singularity happens for it. And the other particle, the other part of the virtual pair, becomes a real particle and leaves the black hole. And if you think about this for a moment, what that means is the black hole is sitting there and it's just ejected a particle, an electron or a proton or an anti-electron. In other words, the black hole with quantum theory is no longer black. It's emitting particles. It's radiating. And it's not just radiating in any way. It's radiating as if it had a temperature. And this temperature, of course, is called the Hawking temperature. Hawking discovers that black holes are hot. Black holes are hot objects, and they're radiating with a particular temperature. Let's go back to our black hole at the center of the galaxy. I told you that was black before, and now I've said they're radiating. But the temperature of that particular black hole, the one in the center of our galaxy, its temperature is barely above absolute zero. And in fact, the temperature of the surrounding material, the gas and the dust around it, is higher than the temperature of that black hole. So it's not, that black hole is not emitting radiation, it's actually absorbing radiation. But if we could find a very small black hole, it turns out that the temperature increases. The smaller the black hole, the higher the temperature is. So if we were able to find a small black hole, we would perhaps be able to measure Hawking radiation directly one day. Irrespective of that point, the overwhelming scientific consensus is that Hawking radiation is real, and this process that I've just described can really happen, or really does happen, and that black holes are hot. There's more. Hawking and others found that black holes obey a set of equations, or a set of laws, which are called the laws of thermodynamics. And these are an established piece of physics that was developed in the 19th century, and they're laws that govern anything to do with heat. So, for example, the steam engine, this great coreless mill, which you can go down to the Science Museum down the road and see today, is governed by these laws of thermodynamics. The laws of thermodynamics are anything involving, capture anything involving heat, to do with things like temperature and work, energy cycles, and so on, entropy. These laws actually have very, very universal applicability. So, for example, when you pump up a bicycle tire, you may have noticed the valve always gets hot. That's the laws of thermodynamics at work. If you release the valve gets cold once the air starts coming out. That's thermodynamics. Thermodynamics tell you how a fridge works. They are very universal, and we know that they are well established and true. And what we've discovered through the work of Hawking and others is that black holes obey these same laws, not roughly these laws, exactly these laws. And so in a very precise sense, black holes are like steam engines. Towards the end of the 19th century, there was another great development in understanding thermodynamics. The laws of thermodynamics were actually found without knowing that matter is made of atoms, without knowing the microscopic structure of matter. And it's quite remarkable that the laws of thermodynamics were established without that information. When that information came later, towards the end of the 19th century, it actually clarified the laws of thermodynamics and made them much more easily understood in many ways. For example, heat. What is heat? So this was just some concept that was used before people had thought about atoms. But we now know that heat has a very precise interpretation as the disordered motion of atoms. If you take a hot cup of tea, the temperature of the tea is determined by how fast, on average, those atoms inside the tea are moving. If they're moving faster, it's hotter. If they're moving slower, it's cooler. This microscopic atomic picture also clarified the important second law of thermodynamics. What's the second law of thermodynamics? The second law says that the entropy of an isolated system always increases. What's entropy? Entropy, roughly speaking, is a measure of disorder. So what the second law says is that disorder, things move from an ordered configuration to a disordered configuration. Disorder increases. Again, we know examples of this from everyday life. You can crack an egg, but you can't uncrack an egg. Things go in one direction, from an ordered configuration to a disordered configuration. let's take another example to do with atoms, which clarifies the idea of the second law. Imagine for a moment that all of the molecules in this great hall were up in the corner of the great hall up there, and everything else was vacuum. Intuitively, we know what would happen is that all those molecules would quickly diffuse and spread out and give the configuration of molecules in the room that we are experiencing right now. The reverse process of all of the molecules in the room bouncing around and suddenly ending up in that corner, bringing the lecture to a premature and grisly end, it's not going to happen. And it's not going to happen because, and this is where this microscopic picture becomes very important, there's many, many, many more ways of distributing all of the molecules in this room in a way that's roughly like we experience. And there's very, very few ways where we can put all the molecules up in the corner of that room. In other words, we experience the air we're breathing right now because it's much, much more likely for the air to be arranged as it is in this somewhat disordered configuration rather than the ordered configuration. Black holes are hot, they're thermal objects, they obey the laws of thermodynamics. There must be some notion of entropy. Bekenstein and Hawking made this important observation, or had this great insight, that the entropy of a black hole is given by the area of the event horizon. The event horizon is this sphere surrounding the space-time singularity, and if you can calculate that area, that will give you the entropy of the black hole. So the second law now, in this more profound way of thinking about things, it's the entropy of all the atoms comprising the hydrogen gas and the galaxies and the stars, plus it's the entropy, the area of the black hole horizon. All of that together increases. That's the new second law that was given to us by Hawking, Bekenstein, and others. So to summarize, general relativity made the astounding prediction that black holes exist, regions of space-time where no light can come out. They are black because no light comes out of them. Stephen Hawking made the great observation, who had the great insight, that when you add a little bit of quantum theory, you go beyond general relativity, black holes are no longer black. They're hot objects, they're like steam engines, and they obey exactly the same laws as steam engines do. In the 19th century, we went further in understanding thermodynamics by appreciating that matter was made of atoms. We appreciated the laws of thermodynamics because we understood better what the microstructure of matter was. So that's pretty much where we are in our current understanding. And it should be clear what the next stage we're looking for. We're looking for the analog of the microstructure, the atoms, which clarified thermodynamics. What are the microstructure? What are the atoms of space-time? What I've been describing is taking a little bit of quantum theory and adding it to general relativity. But to take the next step in seeking the unity of physics, we're going to need a full theory that unifies quantum theory with gravity. It'll be a final equation, much like I said at the beginning of the lecture, an equation where you see not only G and C, but there'll also be another number that appears, or another letter, it's called H bar, and it's the letter associated with quantum theory. We don't have this theory of quantum gravity, and it's something that we're working on. There's many approaches to quantum gravity, and we don't know which one is right, but I wanted to say something briefly to conclude about string theory. The idea of string theory is that the fundamental bits of matter, if you could break down an atom to smaller pieces, inside the nucleus there's protons and neutrons, inside the protons and neutrons there's quarks, there may be more substructure to be discovered at the LHC. If you kept going and going, let's jump to the end of that story, you would end up, the idea goes, with strings. Small little one-dimensional objects that are oscillating. And they're oscillating in much the same way that a guitar string or a violin string oscillates. If they oscillate this way, there'll be an electron. If they oscillate this way, there'll be a proton. And this way, a quark, and so on. So this one string, this one idea of string, allows you to unify all elementary particles. The most interesting aspect of this is that we know that these oscillating strings include quantum oscillations of space-time itself, gravitons. And that's the reason why it's a quantum theory of gravity, or a proposal for a quantum theory of gravity. Over the past 20 years, myself and others have been thinking about black holes in the context of string theory. And there's been a number of important developments. One of them is, perhaps the most important one, is that for certain black holes in the context of this theoretical landscape of string theory, we've understood that their entropy can be explained in terms of a microstructure of strings. A second highlight is that black holes in string theory are actually illuminating aspects about quantum theory itself. So for these reasons and others, many people think that string theory is on the right track. It's on the right track for seeking this unity in nature. The quest that began with Newton, continued with Faraday and Maxwell, had this fantastic contribution by Einstein, and now we don't know how it concludes. But one thing is for sure, and I've tried to emphasize this in my lecture, is that the unification of black hole physics with the laws of thermal physics, the laws of heat, which Stephen Hawking and others have established, everybody almost universally agrees that these will be the central ideas which takes us on that next step for unification. So I conclude with a quote by Abdus Salam, who you heard before was the founder of the theoretical physics group at Imperial College, and he himself made monumental contributions to this quest for unification himself. He unified the electromagnetic force with the weak nuclear force into the so-called electroweak theory. And for this profound work, he was awarded the Nobel Prize for Physics in 1979. He said, "Scientific thought and its creation is the common and shared heritage of mankind." Tonight we've been celebrating the centenary of general relativity, and I hope you agree that we together have been participating right here, right now, in this shared, wonderful scientific heritage. Thank you.
Thank you, Faye. Thank you, Jerome. As I said at the start, we have time for some questions. If you could raise the lights a little bit so we can see if there are hands up. So if you put your hand up if you'd like to ask a question, and we'll get a microphone to you. You'll have to wave your hand because I can't, it's very hard for me to see it. Any hands up? Right at the back. Yes.
Good evening. Thank you for the lectures. Perhaps got a question which each of the speakers could answer one by one. In the search for a quantum mechanical microstructure within black holes, of all the theories that theoretical physicists have so far come up with, namely string theory and causal set theory and other competing theories, would each speaker like to say which theory they think is perhaps the most promising at this stage of theoretical physics research, and why?
We have mics. Well, I think at the end of my lecture, I tried to give a very quick picture of string theory, and in particular highlighted this point that you mentioned, that it does provide some insight into the microstructure of space-time and its connections with black hole physics that I was particularly emphasizing, which I think give people confidence that it's on the right track. But quantum gravity, we don't know what quantum gravity is. There are many different approaches, and I think it's a work in progress. It's a work in progress that began actually in 1925. 1915 was the point when Einstein came up with general relativity. 1925 was when quantum theory was first established. And for basically 90 years, on and off, people have been pursuing this question. There must be a unified theory, one that unifies quantum theory and gravity. String theory has a lot of interesting features. There's other approaches which have interesting features as well, and we will have to see how these unfold. My personal feeling is probably that it's still too early to know if string theory is going to be the final theory. However, there's elements that are very compelling and interesting that make it worth working on now, and they may also survive in an ultimate version which may even replace string theory at some point in the future. We simply don't know. We're following the key clues, and what I was trying to explain in my lecture, the key clues we have so far that everyone agrees on is that black holes are thermal.
So I work on an approach to the problem of quantum gravity called causal set theory, and it's kind of by definition, I suppose that's what I think is most promising, because it's hard to know whether I work on it because I think it's most promising or I think it's most promising because I work on it. It's very difficult to disentangle those things eventually. But it's a theory which takes almost the most simple-minded approach to what Jerome described, which is the problem of coming up with a microscopic atomic explanation for black hole thermodynamics, in the sense that it simply postulates that space-time is atomic. It is discrete. It's fundamentally discrete. It's made of individual space-time atoms. And for that's one of the reasons I think it's most promising, because it really takes it really takes seriously the clues that black hole thermodynamics is giving us about the substructure of space-time. So another reason that I think that it's most promising is the dichotomy that I ended my lecture with, which is this dichotomy between being and becoming. In an atomic theory of space-time, it seems possible to reintroduce to physics a notion of a physical passage of time, something that's very difficult to achieve in a continuous theory like general relativity. So that's another reason that I like causal set theory as an approach.
Would the speakers like to comment on whether they feel there is enough that we know about the universe now that theoretical physics will ultimately come up with the conclusion to the questions you've addressed, or do we need more experimental evidence?
We certainly need more experimental evidence. And I think that the two things go hand in hand. So experiment and theory go hand in hand. So we need to know where to look for the evidence, and the theories will tell us where to look. I don't think the word conclusion is, I think, the wrong one. What we've learned from the history of science is that every great breakthrough leads to new questions. It changes our view of the world in such a way that questions that we couldn't even have dreamt of or asked before suddenly become current. And I think my own view is that I can't see how that could possibly end. Once you have a new vision of the world, a new view of the world, then new questions are bound to arise. So I don't think that this quest can have a conclusion as such, but we can certainly, I think, understand the question that Jerome set before you, that what is the microscopic understanding of black hole thermodynamics. I think that my colleagues and I have complete confidence in science that we will understand will understand the answer to that question.
It's also interesting to just amplify that Einstein, from 1905, spent 10 years looking to unify special relativity and Isaac Newton's theory of gravity. And that was largely driven by theoretical motivation. It wasn't driven by experiment driving his thoughts. There was experimental input. Of course, after general relativity was discovered, there was some experimental input. But the driving force was a theoretical consistency. And I think that quantum gravity, in searching for quantum gravity, that's an interesting model to keep in mind. that it's not going to be, unless there's a big surprise in place, and we don't know if that's the case, it's very unlikely to be driven by experimental data driving the thing. However, we definitely require that at the end. But I think theoretical consistency with these important clues which Hawking and others have laid before us, and these are jewels that are sitting there waiting to be polished and understood in a better way. And that's really their legacy and the things that we're pursuing today.
I think this is a question for Faye. Faye? How do we reconcile the theory of gravitons, which seems like particles, with the theory of general relativity that you've described, which seems geometric rather than associated with particles attracting or rejecting one another?
So gravitons would be part of a quantum theory of gravity. So in that sense, they don't exist in general relativity. So they're not part of this beautiful sort of geometrization of physics. They're something new. They're something genuinely new, which only arise when you think about quantum theory. So they're quantized perturbations of the gravitational field, and indeed they're not part of the geometrical picture of GR.
Thank you very much for your talk. I really enjoyed listening to it, but I get the feeling sort of over the last 10 years that I've been coming to these talks that we don't seem to be making progress, and I feel that what you said this evening, you could have told me 10 years ago. And whilst I don't want to belittle the progress that we've made, the discovery of the Higgs, the oscillation of neutrinos, sort of this talk doesn't seem to have changed in 10 years. Where are we going? We talk about these jewels and these clues, but we still seem to be looking in the same places as we were 10 years ago. Are we making progress? You sort of touched on a few ideas, but this talk and the concepts we're exploring are still the same ones that we seem to be going over and over and over.
I mean, the first point is this is a public talk. And I think it's important to emphasize that, what I wanted to most communicate is that there is real progress, that many people, in fact, I would say even many people of my physics colleagues, are not fully aware of what the driving motivations for quantum gravity are. You yourself perhaps have heard a lot more and appreciate these points. But this notion that black holes are thermal objects is a very profound one that is not fully accepted as essentially as fact. It's not complete fact, but it's a central idea driving things. In string theory, for example, there's enormous progress. If you look at the archive every day, the online repository for all scientific papers, there's 20 to 30 papers that have been produced. Whether the progress in theoretical terms is being made, it's incoherent progress. But the problem, after all, is extremely difficult. It's an extremely difficult problem we've been looking at to try and solve. And we've been solving, as I said, for 90 years. We don't know when the solution will come, and we don't even know how close we are. Again, you can look back to 1915. The last 4 weeks, Einstein was working frenetically to come up with his equations. If you go back a little bit further, as I alluded to in my talk, he literally went down dead ends. He thought he had solved it a few years earlier, and said, that's it, I've done it. And that was just not correct. And he went back, worked hard. These last 4 weeks, he came up with different versions of his final equations before he finally cracked it. And if you look at that period of 10 years from 1905 to 1915, it's very hard to know at a given point when the solution was coming. In fact, with general relativity, the solution came, I think, precipitously. And it came precipitously because of because of his genius, essentially, because of his deep insight to the problem. And one can hope that we are close. We can hope that these incoherent investigations we're making in different directions, built on solid theoretical foundations, whether it's causal sets or string theory, are leading us incoherently, perhaps coherently, to the final answer. That progress is definitely being made.
You sound a bit sad, so let me cheer you up. something that I think is going to happen in the next, maybe 10 years. Well, you're more impatient than that, so maybe you won't want to wait for it. But what I think is going to happen is that data on cosmological data is getting better all the time. And what we're going to see is more and more breakdown between the observations and our current best cosmological model. And in particular, it's going to focus on the value of the so-called cosmological constant. So there are already tensions. So the tension is a physics euphemism for the predictions don't agree with my data. So that the physicists call that tension. So there's now growing tension between between measurements of what should I call it? Let's say the Hubble constant, using data that we take from our surroundings, from today, local data that we take close to us. That means data that is taken from our current epoch, and measurements of it at earlier times. So at the time of the CMB, for example, the cosmic microwave background radiation, there is growing tension between these two measurements, and that is, I claim, and you heard it here first, that tension is not going to go away. It's not going to disappear in systematics. It's going to remain, and it's the problem with our cosmological model is going to focus on the value of the cosmological constant, which it will turn out is not constant. So again, that's news to everyone. I'm declaring it here and now. So just keep your eyes on New Scientist and Scientific American over the next decade. There are going to be cracks in the cosmological model. And I mention that because the theory that I work on, causal set theory, actually predicts that the cosmological constant is not constant, and it has oscillated in value throughout the history of the universe, and would be able to accommodate a cosmological constant that even changes in sign. Now we know that the cosmological constant is positive, but according to the theory of the proposal for quantum gravity that I work on, in the past it could have been negative and surely was negative, and in fact I think that this is going to be able to fit the data better in the future. So there's a lot to look forward to and a lot to be hopeful for and confident of in our ability to make progress in these fundamental questions.
Okay, ladies and gentlemen, I think we are running over time, so on that happy, or at least non-sad note, I'd like to bring the proceedings to close. Before I do that, it goes without saying, Faye and Jerome are world-leading scientists, and it's a real privilege to have them here at Imperial College as members of our wonderful theoretical physics group. But to give talks like that, to be able to explain with great clarity and precision the complexity and significance of general relativity, quantum gravity, black holes, and so on, takes a really special talent. To be able to prepare talks like that with literally just a few days' notice is a remarkable feat. So, ladies and gentlemen, can you join me in thanking Faye and Jerome for a fantastic talk?